Good morning. This is class 7 of classical thermodynamics. In this class, we'll be continuing with the thermodynamics of open systems, and we'll see chemical potential in a system of ideal gases. The chemical potential mu of a system is defined as mu as dou G by dou Ni at constant temperature, pressure, and the number of moles of other components of the system. Okay, and we have also seen that dou mu I by dou T at constant pressure and other components is equal to minus S bar I, and dou mu I by dou P at constant temperature and other components is equal to V bar I. Okay. With this background, let's consider a system consisting of a number of ideal gases. Okay. Let a system be consisting of a number of ideal gases N1, N2, N3, etc. Ni. For an ideal gas, we have PV is equal to nRT. Okay, so for the system consisting of a large number of ideal gases, this equation can be written as PV is equal to, for substituting for N, N1 plus N2 plus N3 plus etc. Ni into RT. From this, what is V? V is equal to N1 plus N2 plus etc. Ni RT by P. Okay. Differentiating this with respect to Ni, keeping Tp and the composition of other components constant, we can write dou V by dou Ni at constant temperature, pressure, and the other components Nj is equal to. Differentiate this equation. Okay, what is the in this equation? We have R, the universal gas constant, which is a constant. T is kept constant. P is also kept constant. Therefore, this equation becomes RT by P into dou by dou Ni of N1 plus N2 plus etc. Ni. Okay. So what is dou by dou Ni of N1, N plus N2 plus Ni etc. Ni, only term which can be differentiated is Ni. So dou Ni by dou Ni is 1, or we can write dou V by dou Ni at constant temperature, pressure, Nj is equal to RT by P into 1, or it is RT by P. Okay. So what is dou V by dou Ni at constant temperature, pressure and Nj? That is the change in volume by the addition of 1 mole of the component I at constant temperature, pressure and Nj. And that is V bar I, partial molar volume. V bar I is equal to RT by P. Okay. So let this be equation number 1. Compare equation 1 to this equation, which can be written as equation A. Okay, equation A is for V bar I and equation 1 is also for V bar I. So comparing equations 1 and A, we can write dou mu I by dou P at constant temperature and Nj. That's what we obtained here. Dou mu I by dou P at constant temperature and Nj is equal to RT by P. Dou mu I by dou P at constant temperature and Nj is equal to RT by P. Cross multiplying, we can write dou mu I is equal to RT by P into dP. Okay, when we cross multiply, the partial differential can be converted into the perfect differential. d mu I is equal to RT by P dP. Okay, so this can be written as this is RT into dP by T. What is dP by P? This can be written as d ln P. Okay, therefore d mu I is equal to RT d ln P. Okay, integrating this equation, when we integrate this equation, we get integral d mu I is equal to R is a constant, T is a constant, integral d ln P. Integrating, since this integration is not between limits, we have to add the constant of integration. What is integral d mu I? That is mu I, and R is constant, T is constant, integral d ln P is ln P plus the constant of integration. Let the constant of integration be mu I 0. Okay, mu I 0. Therefore, this equation becomes mu I is equal to RT ln P plus mu I 0. Okay, and mu I 0 is the constant of integration which depends on the nature of the gas. This equation can be rearranged as mu I is equal to mu I 0 plus RT ln P. This is the standard form of the equation for the chemical potential of an ideal gas. Mu I is equal to mu I 0 plus RT ln P. Okay. In the mixture of ideal gases, we don't talk about pressure, we talk about partial pressures. Hence, this equation can be rewritten as mu I is equal to mu I 0 plus RT ln Pi, where Pi is the partial pressure of the ith component. Okay, this is the expression for the chemical potential for an ideal gas in a mixture of ideal gases. Mu I is equal to mu I 0 plus RT ln Pi. Coming back to the ideal gas equation, we have P is equal to nRT, or for the component I, Pi V is equal to NiRT. For the component I, PiV is equal to NiRT. We don't talk about Vi. This is because in the mixture of ideal gases, we cannot measure the volume occupied by each gas. That's why we talk about partial pressures and not about partial volumes. PiV is equal to NiRT. From this, what is Pi? Pi is equal to Ni by V RT. What is Ni by V? Ni is number of moles divided by volume. Number of moles divided by volume is the concentration. It denotes the concentration of the ith component. Therefore, Pi is Ci into RT. Let's substitute this in the equation for the chemical potential. What was that equation? Mu I is equal to mu I 0 plus RT ln Pi. In this equation, we have to substitute for Pi. Substituting for Pi, we get mu I is equal to mu I 0 plus RT ln Ci RT. Okay. This is in brackets. So, removing brackets, we have mu I 0 plus RT ln Ci plus RT ln R plus RT ln T. This is the product. Since it is a constant, we can write it together. RT ln RT. RT is constant. Logarithm of RT will also be a constant. So, hence, we can club these two constants together. mu I is equal to mu I 0 plus RT ln RT plus RT ln CA. Now this is a constant, and this constant we can denote as mu I 0 Ci, mu I 0 Ci plus RT ln Ca. Now we have chemical potential mu I is equal to mu I 0 Ci plus RT ln Ca. This is the expression for the chemical potential of a component in a mixture of ideal gases in which the concentration of the ith component is Ci. If we are given concentration, we can use this equation. If we are given the partial pressures, we can use this equation. Okay. Now, let's see another form. This form is in terms of Raoult's law. According to the mathematical definition of Raoult's law, we have the partial pressure of a component Pi is the product of the total pressure into the mole fraction of that component. Okay. Partial pressure of a component in a mixture of non-volatile gases is equal to the total pressure into the mole fraction of that component. Okay. Sometimes you put P0 and sometimes you don't. You just write it as P. Okay. From this equation, we have another equation. Mu I is equal to mu I 0 plus RT ln Pi. Substituting for Pi, we get mu I 0 plus RT ln P into Xi. Xi is mole fraction. Okay. Repeating the same procedure that we done before, plus RT ln P plus RT ln Xi. Okay. So, in here, Xi mole fraction is the variable, but the total pressure remains constant. Hence, this term is another constant. Mu I 0 plus RT ln P is another constant which can be represented as mu I 0 Pi. Mu I 0 Pi. Mu I 0, sorry, let's put it as Xi in for mole fraction. Mu I 0 Xi plus RT ln Xi. Now we have obtained a relation for chemical potential in terms of the mole fraction. Okay, this is in terms of mole fraction. The previous one was in terms of partial pressures, and we also derived one equation in terms of concentration. Let's write these three equations together. This is in terms of mole fraction. In terms of concentration, we have mu I 0 Ci plus RT ln Ci, and mu I is equal to mu I 0 plus RT ln Pi. These three equations represent the chemical potential for a component in a mixture of ideal gases. Okay. In these equations, mu I 0 Xi and mu I 0 Ci and mu I 0 are constants. Regarding this equation, mu I 0 Xi is equal to mu I when Xi is equal to 1. Okay, when Xi is equal to 1, ln 1 is 0. This term vanishes, and what is left is mu I is equal to mu I 0 Xi. In this case, when Ci is equal to 1, what happens? This term becomes 0, and what is left is mu I 0 Ci is equal to mu I. Okay. in the first equation